Hi! In this video, we will traverse a graph to find a path between two nodes using MySQL. I drew up this small graph for our experiment. Let's set out for finding a path between, for example, A and I. In order to be able to work with the graph, we need a representation. Let's use a table with two columns, the from node and the to node. Create table. Let's call it graph edges, and one column is the from node with the type of text, and the other column is the to node also with the type of text. Run this. Next, let's add the edges. A simple insert statement will get us started. Insert into graph edges from node to node, and we just list all the pairs. Okay, this is our insert statement. Let's run it. Now we have 12 edges in our graph edges table. But we also want to be able to move in both directions on our edges. To achieve that, let's repeat our edges in the opposite direction using another insert statement. Insert into graph edges from node to node, and this time we are going to use a select, and it's going to be the opposite direction of all the edges. So to node, from the graph edges table. It has duplicated all the rows we had so far, and we should be seeing, when queried, 24 graph edges. This is it. Beautiful. All the edges that we wanted. Okay. Let's start typing up the algorithm using common table expressions, also called CTEs. To declare the goals, I will use two variables. The from node, which I choose to be A, and the and node. Let's rename this to start node. And the end node, I choose this to be I. I also need to run these variables so that they become available in the session. And now we can write our common table expression, which starts like this. With recursive paths, this is going to be the name of the table expression. It will just have one column, a path. And to this path, we will put list of nodes that are on this particular path in a JSON array. But before that, let's declare the end goal. Ultimately, we would like to select the path from this paths table expression. Both recursive and non-recursive CTEs start with an anchor query. For here, I will use select JSON array, which is creating the array from the start node to the to node from our graph edges, where the from node is equal to the start node. Now we have a syntactically correct CTE. We can run this query. And we can see that this is the list of the edges that start from A and go to somewhere at all in our graph. But these are just two element paths. We would like to generate more longer paths. In order to do that, we need the recursive part, which comes after a union all. And so the recursive part, the difference is that you can dereference the common table expression itself in this query. But let's start with what we actually want to do. We would like to append a new element to an existing path. In MySQL, I have to specify the where within the JSON object, which the dollar designates I'm going to append to the root, because our path is just a single array. This is exactly what we are looking for. And so The last parameter is what I want to append. And of course, we will want to append again from our graph edges, but we are also joining up the paths that we already have, this particular path. And so we wanted to join where the from node is equal to the path's last element. MySQL conveniently provides a JSON extract method which can get the last element from an array with this $last index syntax. However, when we run it, we can see this doesn't actually work. It is because JSON extract is not working in the current versions of MySQL in a recursive select. So we will have to work our way around it. To be able to achieve that, I will add an additional column to the table expression, which is the last element on the path. This is really just a repetition of the toNode. So now we have a last column to dereference, and that will actually do the work here. But when we run this query, we will notice that we don't see anything. This is because, let's stop this, there is also loops in this graph. So you can generate new paths all the time by just going in circles A, B, C. And these are going to be all genuinely new paths and longer ones and not go anywhere. To be able to resolve this problem, we will have to add an additional condition that prevents us from going to the direction where we have already been. Now, since I had to terminate the query, I need to rerun these variables. And now we can add the actual condition. So we want to exclude two nodes that are already on the path. We will use another JSON function, JSON contains. So not JSON contains the path and of course the toNode. We will have to quote this with JSON quote. This is it. Now we will not go in circles. Let's see. Yes, there is all the paths that could be created starting from the node A. Small ones, bigger ones, even bigger ones, and ultimately there's 64 paths altogether. But when you take a closer look, it is possible to see that not all the edges end up in I. In fact, there is no filtering for this aspect at all. We need to add that. So I put this to the select, where the last element is equal to the end node that we had in mind. And now we just have 12 rows that confirm this criteria, and all of them are ending in I, as we expected it. Now, just to prove that JSON extract does work when not used in a recursive select, I will replace this last with JSON extract path $last. And we get the exact same result like this. Well, it's possible to optimize on this query if you just need to look for the existence of a path, or you just care about any particular path. You can limit the output to a single row, which will in this case get us the shortest path. And if we check, we can see that indeed A to D to E to H to I is indeed a valid path in this graph. This is it. Thank you very much for watching. See you in the next one.